rush so much given the circumstances. You did a great job of getting through that material in a short time, and we wish you luck catching your flight. You better go. So please, thank Professor Owen. Now I believe I hand over the microphone to Professor Hen Kee Lee. Here he comes.
Ladies and gentlemen, the second plenary lecture is up next, and I'm pleased to introduce Professor Bezan Changratasa, who is a professor of physical chemistry and director of the Institute of Physical and Analytical Chemistry at Wellesley State University in Georgia. Professor Changratasa is also the editor of the Journal of Pharmaceutical and Biomedical Analysis, and as well as a member of the editorial boards of several other journals, including the Journal of Chromatography A, Electrophoresis, and Journal of Separation Science. The title of his talk this morning is Recent Developments on Inertial Separations with Capillary Electromigration Techniques. So let's welcome Professor Changratasa.
Thank you very much, Mr. Chairman, for a kind introduction. Ladies and gentlemen, before starting my talk, I would like to thank the organizers of this symposium for inviting me. It's a great pleasure for me to be here and to have the opportunity to talk this morning to you about the topic you can see on the screen. That's about recent developments on enantiomer separations with capillary electromigration techniques. So, basically, I will discuss two topics. Initially, I will talk about capillary electrophoresis, and then another capillary electromigration technique I have included in this talk is capillary electrochromatography. So, not discussing any of these two topics in details, in this part I will focus more not on the analytical potential of capillary electrophoresis, but on capillary electrophoresis as a tool to understand fine mechanisms of enantioselective or also non-enantioselective intermolecular interactions, some supramolecular interactions. In this part, I will discuss about new generation of co-shell-based silica particles for enantioselective capillary electrochromatography. So just a textbook definition of chirality. Chiral molecule is a type of molecule that lacks an internal plane of symmetry and has no superimposable mirror image. In other words, a molecule is chiral if it is not superimposable in its mirror image. Some statistics about chirality relevant to pharmaceutical industry taken from the recent publication from this year in Journal of Pharmaceutical Analysis. As you can see here, among 127 new molecule entities approved by US FDA between January 2010 and 2014, most of them, more than 60%, have been chiral, and most of the chiral molecules have been commercialized in syn enantiomeric form. So we need chiral technologies in order not only to analyze these compounds, but also to obtain enantiomerically pure chiral compounds. So capillary electrophoresis or electrochromatography is not a useful tool for preparation of chiral molecules HPLC or LC-based technologies can be used for this, but for analysis, capillary electrophoresis is very useful tool. Another quote about the importance of chirality to pharmaceuticals, pharmaceutical industry. You can see here, I will not read this in details, but the point is that chirality is important, especially to pharmaceutical industry, but not limited to pharmaceutical industry only, for some other fields like electronic industry, environmental analysis, food, ingredients, bioanalysis, and so on. So you can see another quote, but from rather old literature, from well-known German philosopher Immanuel Kant. He stated actually some difficulties to differentiate between the objects. Those are not enantiomers, of course, this definition of anything existed about chirality in those years, but those are the objects we call now enantiomorphous objects, like our hands, so earth or some other objects in the nature. These are very difficult to be differentiated, as you can see from the statement. So we try to differentiate them in separation science. So what is important? We need to create in the separation system conflict like this, you can see here. So right foot fits well to the right shoe but does not fit to the left one, and you need something similar to have in the separation system. Or if you take the right glove, it will fit to the right hand but will not fit to the left one. So if you don't have conflict like this in a separation column or in separation capillary, you want to use for separation, you do not have any chance for success. Fundamentally, this is impossible. Conceptually, if you don't have chiral selector, you will not manage any chiral separation. So you can see some attempts or some papers have been published in literature to do some chiral separations with very highly efficient chiral columns, chiral selectors, and so on. This is actually conceptually impossible, as I mentioned, and a priori failed task. So, which are the techniques where we can realize such kind of conflict? As I mentioned before, we can use gas chromatography, high-performance liquid chromatography, supercritical fluid chromatography, and these two capillary electromigration techniques, capillary electrophoresis and capillary electrochromatography. In this presentation, I will focus on these two, electrophoresis and electrochromatography. So let's go through the electrophoretic part of my presentation. Why shall we use capillary electrophoresis? We have very high plate numbers in this technique. We have extremely high flexibility in order to change chiral selector. You can change chiral column, of course, in HPLC, but this is much easier to be done in capillary electrophoresis because you just need to replace one buffer with the other one, and then you have the new chiral selector in the system. We can easily adjust the concentration of chiral selector. This is impossible in HPLC since you have the fixed concentration of the chiral selector on the chiral packing material or in your chiral column, and we can easily combine chiral selectors. We can combine chiral columns also in HPLC, but it's not easy task due to higher back pressure in the system you can generate. Also, the compatibility of two columns with each other, because you may separate something in one column, you can lose the separation on another one. This is rather easy to be done in capillary electrophoresis. We have short method development time in capillary electrophoresis. We can easily adjust the enantiomer migration order. Again, this is rather difficult to be done in chromatography because in chromatography actually enantiomer elution order, we don't call this migration order in chromatography, elution order, is determined by the affinity of enantiomers to the chiral selector, and this is not always the case in capillary electrophoresis. In capillary electrophoresis, you have the alternative tools to adjust enantiomer migration order without changing the affinity between selector and selectant. This is impossible in HPLC. we can easily manipulate with separation selectivity, not thermodynamic selectivity of separation that is given by the binding constants of enantiomers of the given compound with the chiral selector, but separation factor. So actually, correlation between thermodynamic selectivity of recognition and separation selectivity in HPLC is very strict, given, and separation factor can never exceed thermodynamic selectivity of recognition in chromatography, but this is possible in electrophoresis. So these are the advantages of capillary electrophoresis compared to chromatographic techniques for separation of enantiomers. Capillary electrophoresis is a very powerful tool, not only for analytical scale separations, but also for investigation of fine mechanisms of enantioselective intermolecular interactions. Actually, we can leave this word enantioselective out of the sentence, and this is actually true not only to enantioselective, but also to non-enantioselective interactions. And the major reason why is that we have very high plate numbers in capillary electrophoresis, and with this technology we can detect those intermolecular effects, intermolecular interactions, which we may easily overlook with either spectroscopic separation or non-separation techniques. So you can see this statement given here. So what are the advantages of capillary electrophoresis from the point of view I discussed? Not from the analytical point of view, but from the viewpoint of understanding enantioselective interaction mechanisms between selector and selector. Capillary electrophoresis allows very fast screening of selector and selectant pair in order to prevail the most interesting of them for further mechanistic studies. So you can screen, of course, this kind of interactions also in HPLC, but in capillary electrophoresis you can do this faster. There is no other instrumental separation or non-separation technique that can compete with capillary electrophoresis from this point of view. The high peak efficiency in capillary electrophoresis enables to observe enantioselective effects in those selector-selectant interactions which are invisible by other separation techniques. What I'm talking about here is that since we have very high plate numbers in capillary electrophoresis, you can see separation in this technique when the thermodynamic selectivity of recognition is very low. If you imagine you have thermodynamic selectivity of recognition 1.01, in GC you will not see separated peaks. In HPLC, of course not, but in capillary electrophoresis you can see still these two peaks separated with binding constants, let's say 100 and 101. With other techniques, you will not see two peaks. In capillary electrophoresis, you can still see two peaks, so you can see the recognition, and that kind of recognition you would easily overlook with other techniques. And this is actually the statement made here. The small thermodynamic selectivity of recognition can be transformed into high separation factor in capillary electrophoresis. Again, this is impossible to be done in chromatographic techniques because in electrophoresis you are using the mobilities, and by this way you can generate from given but very low thermodynamic selectivity of recognition very high separation factor that is impossible in chromatography, where, as I mentioned, the separation factor can approach to the thermodynamic selectivity of recognition maximally, but never exceed that. In capillary electrophoresis, this is possible. And capillary electrophoresis is also more flexible than chromatographic techniques are in order to adjust the separation factor and enantiomer migration order. What are the disadvantages? Capillary electrophoresis does not provide any information about the structure of complexes. And then you need to use some alternative techniques. What are these techniques? We can use X-ray crystallography. What's the advantage of this technique? You get the information about the structure of selector-selectant complexes, but disadvantage is that this is a solid phase technology, and in capillary electrophoresis we are working with liquid phase. So you have the process in liquid phase, and then you want to correlate this with the structure you are observing in the solid state. So this is disadvantage. NMR spectroscopy provides information about the stoichiometry, binding constants and structure of selector and associates in solution. But if you have mixed complexes, you cannot use NMR spectroscopy. And this is the problem of NMR spectroscopy. MS provides information of identical complexes, so even if you have the mixture of complexes in the system, you can use mass spectrometry to characterize those complexes, but you don't get direct structural information in mass spectrometry. So NMR has the advantage of providing direct structural information of selector intermediates complexes in solution, but we cannot use for mixed complexes. Mass spectrometry we can use for mixed complexes, but we don't have direct structural information. We can use molecular modeling, molecular mechanics calculations. What is interesting with this, actually you can look for the correlations between NMR determined structure experimentally and computed structure based on molecular modeling or molecular mechanics calculations. But the most important application of molecular modeling is to compute the forces. So not just to look for the correlations between experiment and theory, but to compute intermolecular forces involved in binding, but more important for chiral separation is to compute the forces involved in chiral recognition. Forces involved in binding and forces involved in recognition can be different, and we need to pay attention to this. So what are the tools actually? We are doing our research based on synthesis, separation, and analytics, spectral techniques, and computation. And you will see in slides I will discuss something about this. So now you can see on the screen the major equation determining the mobility difference for binary mixtures in the electrophoretic separations in general. This is not about enantiomer specifically, and not about capillary electrophoresis specifically, but we can use the same equation for determining the mobility difference in enantiomer separations performed by capillary electrophoresis. And in order to observe two separated peaks, this term, mobility difference between two enantiomers, has to be non-zero, different than zero. And that's the concept. So, in the early literature of capillary electrophoresis, this equation was recognized, of course, and it was assumed that diastereomeric associates have the same mobility. So, in this equation, I did not discuss in details. Actually, the major terms are the mobility of the free analyte. This is the mobility of diastereomeric complex between analyte and chiral selector. This is one enantiomer. The mobility of the another enantiomer complex with the chiral selector. And so if you assume that these two are the same or equal to each other, then you can simplify this equation. You arrive to this one, and this was actually the equation well recognized when understood in capillary electrophoresis already in the early days of development of chiral capillary electrophoresis. And this was considered as the major equation describing mobility difference between the enantiomers and based on this separation factor in capillary electrophoresis. And actually, this equation assumes that the affinity of two enantiomers with the chiral selector are different. So the separation is based on the different affinity of two enantiomers with the given chiral selector. This is actually separation mechanism also in chromatography. In all chromatographic techniques, it is GC, LC, or SFC. But in capillary electrophoresis, if you assume that the mobility of two diastereomeric associates are different, then the binding constants can be the same. So you can come to the conclusion, and this was what we have made about 20 years ago, that in capillary electrophoresis, in difference with all chromatographic techniques, you can observe two enantiomers separated, even in the case when the binding constants of both enantiomers with the chiral selector are the same, and we have defined that actually derived this equation that tells you something like that. So, and this statement was made, as I mentioned, about 20 years ago. It was very, very confusing, very strange, because as I mentioned, in HPLC something similar is conceptually impossible. In capillary electrophoresis, this is possible. So this is the equation. You can see that equation actually in very correct form as I see here. So if you assume that the binding constants are different, you have this principle determining the separation of enantiomers in capillary electrophoresis. But if you assume that the binding constants K1 and K2 are the same, but the mobility of diastereomeric associates are different, then you will see still separation in capillary electrophoresis. And this was the concept we have introduced about 20 years ago, as I mentioned. This was the hypothesis, because we could not prove this instrumentally in those days. So later on, just quite later, after about 15 years, we found some experimental results giving us the idea that this should be the confirmation of our hypothesis made in 1997. So in this particular case, you can see concentration-dependent reversal of enantiomer migration order in capillary electrophoresis. For this antimycotic drug ketoconazole, actually studied also in this country by one of the organizers of this symposium, this compound. So you can see at the lower concentration of hydroxypropyl beta-cyclodextrin, we are observing one enantiomer migration order. At the higher concentration, opposite migration order. At the electrostatic concentration, these two effects cancel each other, and you don't observe any enantioseparation. Actually, I will not discuss maybe this in detail, but you can see that based on NMR spectroscopy, capillary electrophoresis, some other techniques, we could prove that at the lower concentration range, we have affinity-dependent separation. So this is actually the kitchen behind. So we are trying to determine stoichiometry of the complexes based on NMR, nuclear magnetic resonance studies. So you construct Jobs plot just to prove that complex stoichiometry is 1-to-1. Then if you prove that complex stoichiometry is 1-to-1, then you can use Scott's technology, Scott's technique, to compute or to calculate binding constants. And you can see the binding constants here for both enantiomers with the chiral selector. And if you go to capillary electrophoresis, so what is the advantage of capillary electrophoresis compared to NMR spectroscopy for this particular research? Actually, we are using two techniques, NMR spectroscopy and capillary electrophoresis, to determine the binding constants. Since those binding constants are very critical to our conclusion, we use two techniques. So double checking the binding constants, we can determine in NMR with capillary electrophoresis. But another advantage of capillary electrophoresis is that capillary electrophoresis also provides the mobility. Information about the mobility of diastereomeric associates that enters the equation I mentioned before. So we need not only binding constants, we need also the mobilities of diastereomeric associates, and we get that information not from NMR spectroscopy, but from capillary electrophoresis. So you can see now binding constants of two diastereomeric associates, and you can understand that in this range, separation is based on the binding constant, on the affinity of enantiomers to the chiral selector. But if you consider the mobilities determined based on these plots in capillary electrophoresis, you can see that in this higher concentration range, the separation is based on the mobility. So that we have affinity-based separation range at the lower concentration, and then we have mobility-based separation range at higher concentration. As you can see, mobility-based separations are even better than affinity-based separations. This mechanism was recognized in capillary electrophoresis, but this one was neglected, and as I mentioned, about 20 years ago, we made the hypothetical statement that this is possible, and later on, we could prove that is really possible in capillary electrophoresis. So later on, actually, in cooperation with Wolfgang Thornen's group, we computed based on the mobilities and affinities, you can compute, of course, what you get at a given concentration of chiral selector in the system, and you can see that the experimental and computed results fit each other very well. So we have very good agreement between computation and experimentally determined migration or the co-migration and reversal of the natural migration. So let's discuss now these techniques. How can we use those techniques to understand more about chiral separation mechanism, capillary electrophoresis? So this chiral drug, ketamine, is quite interesting because for base of this compound and for the salt, you have different sign of rotation, optical rotation. And optical rotation is actually still the major pharmacopoeia technology to determine the optical purity of chiral drugs. If you use that technology, you will be very confused in this particular case, because as I mentioned, if you observe base, you get one sign of optical rotation. If you transform base of the same, with the same absolute stereochemical configuration to the salt, then you will see the opposite sign of optical rotation. So this is another application of X-ray crystallography. And you can see that we are using two cyclodextrins, one chiral analyte, chiral drug, beta cyclodextrin and trimethyl beta cyclodextrin. You can observe opposite affinity of enantiomers towards these two cyclodextrins. In order to understand what is the reason of this, we try to understand the structure of complexes, and you can see in the case of beta cyclodextrin, we have sandwich type complex, brompheniramine molecule entering the cavity of one of the cyclodextrins and malleate, that's the counter ion of brompheniramine in this particular case, occupying the cavity of other cyclodextrin molecules. So the stoichiometry of this complex is two cyclodextrin to one chiral analyte, but if you take another cyclodextrin now, trimethyl beta cyclodextrin, you get just 1-to-1 complex, and the structure of complex is very different from this one. Aromatic part of the analyte is entering the cavity of cyclodextrin in this case, but alkyl part of the analyte is entering the cavity of trimethyl beta cyclodextrin. So we are observing the effects in capillary electrophoresis, and we try to explain those effects based on X-ray crystallography in this particular case. This was just one example. Of course, I am not discussing all examples from our study, just to show you what are the limitations and what are the advantages of each technology. This is NMR spectroscopy. As I mentioned, we can use NMR spectroscopy nicely to determine the stoichiometry and binding constants of complexes related to separation in capillary electrophoresis. But the limitation of this technique is if you get the mixed complexes like we have here, then you cannot use NMR spectroscopy to understand anything about complex formation of binding constants. While we conclude that we have mixed complexes, not only one uniform complex in the system, but at least two. Because if you have one uniform complex in the system, chemical shift of the signals has to go only in one way. And you can see that it goes to one way, but it turns back again. So this is actually very nice and non-selective effect, because we have not non-racemic but spiked sum. It has one of the enantiomers twice more than another one. So you can compute from there stoichiometry, you can compute binding constants theoretically, but in this particular case not, because this proton NMR results show that we have mixed complexes. And as soon as you arrive to the mixed complexes, you should not use NMR spectroscopy anymore. You shall try to go to other techniques. So let's discuss about mass spectrometry. And you can see that mass spectrometry, even in the case of having mixed complexes in the system, provides information about each complex. You can see that we have one-to-one complex between beta cyclodextrin and dimethyl chiral drug, and then we have 1-to-2 complex, and both can be observed. But this technology doesn't provide you direct structural information, we will see later on. So molecular modeling, again you need to be very careful with this, because you can see that experimental migration order is one, and computing migration order does not fit actually what we observe in experiment. As I mentioned before, capillary electrophoresis has the advantage that you can see recognition even with very low thermodynamic selectivity. If the binding constant difference is very low, you will still see separation in capillary electrophoresis. But there are no techniques now to compute the energies with the 1 kilocalorie per mole difference. So if you have 1 kilocalorie difference between the binding constants, you will see two peaks. You will see recognition in capillary electrophoresis. But molecular modeling or current molecular mechanics calculations, force fields, do not allow you to compute the energy as precise. It is relevant to capillary electrophoresis separations. So we have done a lot of attempts. Mostly we fail, but sometimes we are quite successful. So what is the mistake in this kind of computing here? The computation is performed in a vacuum, while the separation is performed in aqueous medium. You should be very careful with such kind of mistakes you can make easily, because computation in vacuum is much easier than computation in aqueous system. If you put now water box in your computation, you can get the results that correlate nicely with the experiment. So more complex, longer computation now, but you get very good correlation between experiment and computation. So this needs to be considered when you are using molecular modeling calculations. So now let's go a little bit deeper with the application of these alternative techniques to understand something about the structural complexes. So we will discuss now about nuclear Hauser effect-based techniques we can use in the liquid phase to determine the structural complexes. Why this particular example? We have clenbuterol chiral molecule, 2 cyclodextrins, and you can see opposite affinity of enantiomers towards these 2 cyclodextrins. And then after seeing this difference, the cyclodextrins in this particular case are beta cyclodextrin and heptacase diacetylated beta cyclodextrin. So on the secondary ring of cyclodextrin, actually acetyl groups are put in position 2 and 3 in all glucopyranose units. So that's the difference between the structure of these 2 cyclodextrins, and as the result of these differences, you get different affinity of enantiomers. So R enantiomer has less affinity than S towards beta cyclodextrin, while it is opposite in the case of acetylated one. We try to understand the mechanism of this phenomenon in order to get some explanation why we observe that. So this is just a very simple proton NMR spectra of those 2 complexes, and you can see there that in the case of beta cyclodextrin, aromatic part of analyte is more affected, but in the case of heptacase diacetyl beta cyclodextrin, alkyl part of the analyte is more affected. Why we conclude that? You get some splitting of signals. You see 2 enantiomers here. So in this case, if you try to see the similar, in the case of another cyclodextrin, acetylated one, you will not see any effect on the aromatic part. In this case, you don't see effect on alkyl part, you see effect on aromatic. And in opposite to this, you see effect on the alkyl part, you don't see anything on the aromatic part. You can already think maybe aromatic part of the analyte is included in the cavity of beta cyclodextrin, while alkyl moiety must be included based on this simple proton NMR experiment in the cavity of heptacase diacetyl beta cyclodextrin. This is actually intuitively so, but you need to prove this. And to prove this, we need to perform Royce experiment. I will not go deeply now to explain about the principles of Royce experiment. You are just looking for the fitting between selector and selectant, irradiating, actually giving some energy to the protons, let's say, in the analyte, and observing response on your selector. So you can put, based on Royce experiment, selector and selectant groups on a certain distance in the space to each other. Since you will observe such kind of Royce effect only on the distance from 3 to 5 angstroms. If non-covalently bonded groups do not approach to each other as close as 5 angstrom at least, you will not see any response. When you are irradiating one, you will not see the response on the other. So this is the basic principle. If some of you have the questions, we can discuss, of course, in more details. So in the interest of time, I will go now rather faster, just to the results. So we are performing such kind of proesis study for both complexes, clenbuterol with beta-cyclodextrin and clenbuterol with diacetylated cyclodextrin. And the conclusion is that in both cases we have inclusion complexes. In both cases, analyte enters the cavity of cyclodextrin from the wider ring, but in one case, aromatic part is included into the cavity, while in other case, analyte turns and enters the cavity of cyclodextrin with the alkyl moiety. So you see different in recognition. You can observe this based on papillary electrophoresis, and then you can explain this based on NMR experiment. Why this happens? Because you can see very significant difference in the structure of diastereomeric associated, giving this separation and this one responsible for this kind of separation. So we can compute actually the structures I mentioned, and you can see in this particular case very nice correlation between NMR experiment and molecular model calculations, since in this case this is a complex with beta-cyclodextrin. You can see aromatic part of the analyte included into the cavity. So this is computed structure, but as you have seen before, the structure is very similar based on proesis experiment in NMR spectroscopy. So this is refined structure of the same complex, aromatic moiety of the analyte entering the cavity of cyclodextrin. If you go now to the same analyte complex now with diacetyl beta-cyclodextrin, computed structure, again you will see alkyl part is included into the cavity. So this is refined on the next slide. So alkyl moiety of the analyte included into the cavity. So as I mentioned, you can compute the structure. Then you can determine the structure experimentally, you can look for the correlations. You may be quite happy if you see the correlations, like we see here. But the major goal for the computing should not be such kind of correlations. We shall go further, we shall compute particular forces. Electrostatic, van der Waals, dipole-dipole interactions, in order to understand which of those forces are responsible for binding and which of them are responsible for chiral recognition. As I mentioned before, the forces responsible for binding should not necessarily be the same as the forces responsible for chiral recognition. They may be different. So, again, in the interest of time, I need to skip some of those slides. We are using very similar methodology to various cases. You can see that we have studied many different chiral drugs. Sometimes we observe that the inclusion complex formation that is considered necessary for chiral recognition in cyclodextrins is not really necessary. You can see there are two cyclodextrins. I will discuss maybe a little bit about this case. So you can see very nice enantiomer separation with heptacase diacetyl sulfated one, and not that nice, but separation is there with dimethyl sulfated beta-cyclodextrin derivative. So this one separates well, this one also separates, but not that well. And you can see that with the well separated one, we don't have any inclusion complex. The complex has the external structure. We have external complex here, inclusion complex here. So sometimes when the external complexes are formed, you may observe a better separation if you compare this with the complexes, inclusion type complexes. So inclusion was considered as necessary prerequisite for chiral recognition with cyclodextrins, but as you can see there, sometimes an external complex formation may provide better recognition. So an anti-selective proesis experiment is a very important one, but again, very technical detail. Maybe I don't need to go in details here, but what we do actually, we try to irradiate protons and neutrons selectively in this particular case in an light, and then you observe the response on cyclodextrin protons. So higher response means that this complex is tighter. So the proximity between selector and selectant is higher in this particular case rather than here. So if you observe now an antimal migration order, so more tightly one will give you the migration order you can observe here. So again, you can derive the structural complexes. So this is actually first case where we managed to perform an anti-selective Roy's experiment nicely correlating with the enantiomer affinity pattern or enantiomer migration order observing capillary electrophoresis. So Roy's experiment is really very powerful, very useful technique to explain observations you have in capillary electrophoresis. So now I'm going to go in the final part of my presentation to partial silica. And you know what is the difference between fully porous and partial type silica. In fully porous silica we have actually silica particles which have the pores, also true pores, but in the case of pore shell we have non-porous core and we have porous shell. So how does this relate to capillary electrochromatography? When we started to use capillary electrochromatography about 22 years ago, we were observing very impressive results. Higher plate numbers in capillary electrophoresis and electrochromatography. You can see this here. We have lower plate height, almost twice, 2.5 times, 2.5 times lower plate height in capillary electrochromatography. So sharper peaks than in capillary liquid chromatography, or we call this now nanoliquid chromatography. So another important advantage of electrochromatography is that when you go to higher flow rate, you don't lose that much in plate numbers, while in nanoliquid chromatography you will lose plate numbers in very short time. Time in this particular case means the higher speed. If you go to higher speed, you get lower plate numbers in nanoliquid chromatography, but if you have electrochromatographic migration mechanism then you don't lose the plate numbers. Actually, these experiments are performed exactly the same instrument, same experimental setup, same color. How many minutes do you give me? One more? Only one. Thank you very much. So, this is the advantage of electrochromatography. How do we try to explain this kind of advantage? We say that in electrochromatography, we have flow through the pores. And you can see this actually, that we get much lower C coefficient in this one dentate type equation in electrochromatography compared to nanoliquid chromatography. If you compare C terms, so you will see low number for CC compared to CLC or non-LC. And this was the explanation. Why this explanation conflicts now with the application of partial type particles? In partial type particles, as I mentioned, you have solid core. So you may not have the perfusive flow through the particles. So an explanation of higher plate numbers in electrochromatography was flow through the particles. Now with partial particles, you may not have that kind of flow through the particles. So why partial type silica has to be used in electrochromatography? So again, I shall skip some of the slides. But you see quite confusing results. Let's say electroosmotic flow generating in the packed capillary columns with partial silica is higher than with totally porous silica. This should not be the case if the flow is generated through the pores. And moreover, plate numbers are higher with partial type particles compared to total porous particles. So this was actually the part I see Mr. Chairman standing there. So I will just conclude that a priori or theoretically, you may think that coarser particles may not provide any advantage, at least over totally porous particles in capillary electrochromatographic experiment, but experiment shows something different. So we still need to think about this and to explain effects like that. So I will not read the conclusions. Electrophoresis is strong technique of coursework, analytical scale and anti-separations. We understand the dynamics of electrophoresis. We don't understand thermodynamics that well. It's stated here, but in electrochromatography we still need to think why we have advantages of electrochromatography compared to nanoliquid chromatography, where the flow comes from, and how does the flow contribute to the generation of higher plate numbers. I would like to thank some of my students, my colleagues, and thank you very much for your kind attention. This was the information about the special issue of electrophoresis I'm editing on chiral separations. So the deadline is quite close now, but if you have manuscript ready, you can still manage to submit until November 15 or ask for some extension I could provide you. Thank you very much for your attention.
Thank you, Professor Chirality.